All right. Yeah, let's first bring up our notes from last stream yesterday. Wiggle it around. Okay, so then here's the plan. Well, this one I'm actually gonna take this line right here. I'll put the stuff. I'm just gonna like kind of move it later because I want to kind of keep everything in the policy right now. Kind of because last stream we are doing policy, so let's kind of be in the policy world. Like we were previous in the game state world, and now we're kind of in the policy world. Okay, so then here's like the plan for today, I guess, like this stuff right here, or maybe everything. Test conversion of policy to a vector and vector back to policy. Parts, parentheses, parts of convert policy to tensor and get policy in value. I'm thinking like a loop full circle test as these two functions are kind of inverses. So let's just take that away. And then let's just so what do I mean by that, right? So if we take a step back and we look at like Monte Carlo tree search, or let's so right now, like I remember like there's a old whiteboard which I had which kind of like showed the big picture. Like given a state, right? Given the game state, we kind of, it's like a chemical reaction with like a net catalyst or whatever. And then like given the game state, we get two things. A policy vector, policy tensor, policy vector, or what did I call it in my notes? Given a policy to a vector and vector back to policy, right? So policy tensor or policy vector of a size, like the shape is like 2400, right? 2400. Why 2400? Like a num or like some number of that, which is the number of durs, 8 times 15 times 20. Right, 8 is like the number of directions, kind of analogous to channels in RGB. And like 2 for Connect 4 because it's like player 1's coins and player 2's coins. Here we have 8 directions to wait, no, sorry, I'm conflating things. This is not channels, that's for the input, sorry. This is just the output. Like, I mean, kind of like an image stack, like flattened to 2400. But anyways, and a value, which is singleton list. And by that, I just mean a list with one element, just one number between -1 and 1, the tanh output from the activation function. Right, -1 means current player loses, and then like, or is about to lose, or is a losing position. And then +1 means, you know, that the current player is on track to win, or it's just, I mean, yeah, that's just what it means. It's a very good evaluation from their perspective. So from this vector, we have like a function called a get. Oh wait, no, cd BumperCoins bot. Get status. Okay, good. Everything is clean. Get log. Just we were just doing some testing in Scratchpad for the last two commits, last two streams. Get status. Oh, wait, what am I doing? Less net.ts. Okay. So we have get policy and value, right? Which takes in the game state, takes in the neural network, and then it does the prediction on it, right? So it takes the representation, it just calls predict, and then we're kind of given like this, the policy data and the value data, right? So this policy data, this number right here, is exactly like this policy vector right here. It's a size 2400. And what? And what? And then from this policy data, we're basically like this whole code right here basically is filling up legal moves with probs. So from our policy data, we're basically extracting out a and given our game state, we're converting this to a policy, right? So from this, we have like get policy and value, like get policy and value, get policy and value, and this gives us a policy object, right? So this is like so this is basically kind of left to right, right? But then, like, this isn't, like, let's say, like, during MCTS, right? Like, Monte Carlo tree search, we like, when we're creating the node, when we hit the leaf node or in the very beginning, when we're creating the roots, like, we're basically calling the net on the game state. And from the policy, we're building our Monte Carlo MC edges, right? The actions that we're going to take and their weights. So then that's our policy. And we kind of, like, we kind of use that, like, the whole UCB stuff to compute our most promising edge to take, our most promising action to take in the tree search. And once the search finishes, we are finally given an improved, hopefully improved, policy. And then from the policy, we're kind of like, we're going to train on that, right? So then from a policy, basically, like, from this policy, eventually, what we're going to do is we're going to get a policy. And then we're going to have to convert this back into a policy vector, right? Like, this policy goes back into a policy vector when we are doing the training, and when we're actually training it, right? Like, when we're doing like that, we have this function right here. Like, when we're doing train model, we pass in the x's, the y's, ones, and y's, twos. Like, ones and twos are for policy and value respectively, I believe. Yeah, see, y1s, we convert policy to tensor, right? Where the example, like, this whole thing about example is just a training sample, which is in training sample we get during self-play, like during a whole bunch of Monte Carlo tree searches, I think like 1,000 or whatever number of MCTS simulation variable is. So basically, like, anyway, so the point is that we have this convert policy to tensor. So it's like get policy and value and convert policy to tensor are kind of inverses of each other. Convert policy to tensor. So basically, get policy and value is kind of in this kind of in this block right here, where we're kind of building our legal moves and probs, basically where we're building our policy. This is essentially like convert tensor to policy, where I believe like this is our tensor and then we're data syncing on it or whatever. Like, this is kind of like our vector, our tensor, this policy data, or maybe its prediction of 0. And then we're converting that into a policy. And then from here, we kind of going back. And remember, to convert stuff, we also need like a game state, like there's like an implicit GS in these arrows too. Like, we're using this function parameterized with GS, and this function also parameterized with the same GS. So yeah. So that's what we want to test. So I'm thinking what we're gonna do is we actually have a policy right here, right? Like this right here, let's look at our kind of like our scratch pad or kind of like our test files or our tests. So here's a starting game state, player 1's turn. Player 1 elects to move this coin a bit up, so then we get this resulting position. And then it's player 2's turn. 30 ticks later, then player 2 chooses to take his king, and for some stupid reason he's playing the bomb cloud and advances his king a bit more to the center. Well, actually, no, there's an obstacle right here, so that might actually be smart. Who knows, given the obstacles. But anyways, player 2 makes an unusual move, and now it's player 1's turn. So player 1's turn policy is probably to like do some flank attack or something, like, because the king's exposed, his defenders are like kind of misplaced. it kind of makes sense for player 1 to kind of go on the offense a bit. So here's like the policy I just kind of chose, 0.3, 0.5, 0.2. Again, they sum up to 1.0, and like here's kind of like the policy. And we actually have the policy, right? So what we should do now is what I want to do now. Actually, let's open up the notes. So we're thinking of full loop circles. This whole notion of a loop or a circle, I kind of like basically kind of like visually showed in this kind of diagram here, how like from policy, vector, and policy are kind of like, they're kind of like one-to-one. We just have these two conversion functions and the game state, and we're kind of like doing the same logic. Again, because like the game state, right? Because fundamentally, these both are leveraging or in like this notion of coin discretization, right? Our discretization function, the very same one we used in our game state discretization to represent a game state object as a suitable input for our net, like right here, is actually like discretize or convert GS to image or discretize that. But ultimately, the building block for all of this is actually like the convert coin to discretized, or wait, let me actually open that. Like this get discretized coordinates. Like this is the heart of everything, because like ultimately like whatever objects we have, like they have like floating point, or like the actual coordinates are I guess fixed point, but like there's a fraction, but then we're kind of discretizing it to be a suitable input. So ultimately like this function is gonna like, this is at the heart of everything. Like if you look at get policy and value, it's like kind of using discretized coordinates, right? On the coins. Again, we need the game state too, right? I've talked about it a bunch of times. And then kind of like the reverse one where we're kind of like getting like, so here's the tensor to the policy, and then here's the policy to the tensor. And again, they both have GS, and they're both getting the discretized coordinates. So like that's kind of why they're kind of inverses. And I think I remember kind of computing the index or something somewhere. Somewhere I remember doing that in Scratchpad. I think the first block that I commented out. Yeah, let's just let's just open up or status, make sure there's nothing edited. Now it's actually, yeah, so like this first block where I first kind of created the Scratchpad file, I just populated initially like this whole stuff, and then async because we're calling a wait on the model, and then we're kind of like, it's like declare stuff and then do stuff. So anyways, the point, actually I forgot the point. I was looking at my notes, right? So yeah, the point, so we have a full loop where like these functions are kind of inverses. So like it kind of makes sense to kind of like test them out and like use them both for testing. So let's see. So start with a custom policy, maybe same policy from symmetry test, and that's correct. I have a policy to work with from symmetry test. And that policy right here is this policy right here. This is the policy like 0.3, 0.5, 0.2, right? Like these sorry about that. Like 0.3, 0.5, 0.2, and so forth. So yes, so these three lines kind of build up. So like right here, we're kind of building up this policy. So now we have a policy to work with, so that's great. Then convert it to a tensor, or maybe just a number array. Then convert that to a policy and verify we get the same policy. Like we could extract some code from the two functions to create helper functions that operate on number. Okay, let's put some gapping here. Now, one thing actually that's kind of cute is what we can do. I mean, we can print out the policies like we did in the symmetry test. Is like we could actually maybe even convert the policy back into a tensor and verify the tensors match if we want to avoid like kind of console printing out the policy or manually comparing policies. That's kind of cute, right? Like But I don't think so. I mean, we manually compared the policy kind of console log output for symmetries, so like might as well be consistent and do it here. So anyways, so basically like what I'm saying is we have a policy, right? We have this policy, which is kind of like shown by like these three arrows, like given this game state where it's player one's turn to move. We're going to say that he kind of wants to move this coin here with like max probability. Then he's kind of interested in maybe moving here. And he's a little interested, but not so much in moving this one because this one is already advanced a bit, right? In the very first move, we kind of moved that. So this one's already closest to the enemy king. So we're kind of saying that like we really want to move this coin as opposed to this coin. And then when it comes to moving this coin, we're thinking that this is the way to go. Again, this is just an arbitrary policy I chose. So now we have a policy to work with. That's our policy, right? It's a working policy. And what I'm saying to do in my notes is we take this policy, right, and we convert it to a tensor, right? A vector of size 2400. Like we use the game state to give the locations of these coins, particularly this location, that location discretized. And from that, we build our and from a policy, we're basically converting it to a tensor, like when we're training or whatever. Like if this is our like resulting policy as a result of the Monte Carlo tree search, so like after that, we get this improved policy, our working policy, and then we convert it to a tensor, right? Then what we can do to test that we convert it to tensor correctly is we can take that tensor and we can given the game state, we can actually extract a policy from that and then verify the policies match. So let's call this policy 1 or policy original or just P for policy. Then we convert it to a tensor. Let's call that T. And from the tensor, we can actually go back to the policy, like extracting the logic from a get policy and value. We can like kind of like create a helper function that like this is great. Like yeah, we can extract some code from the two functions, operator number, or just we extract some like get policy part of the get policy and value. So let's take so to recap, we have a policy P, and from P we go to T, which uses convert policy to tensor, and from the tensor we can kind of like use get policy on it, extracting the logic out to get a policy again, right? And then we can console.log, like let's call that policy P2. So P to T and then T to P2, we can kind of manually compare P and P2 to make sure that the policies are the same. We should also make sure they point to different objects. And then what we can do if you're kind of feeling cute, I guess, is like this thing which I just had right now. This thing is like take P2, convert it to a tensor T2, and then verify that like T1 equals T2 in case there's some like helper method in like some equality dot equals check in a TensorFlow.js if we're kind of like being super fancy. Or we can just manually compare the policies by hand, which I think I'll just do. So, okay, let's just kind of like test that. So basically by testing that, we're basically doing a test of like these two functions. And once these two functions are tested, I think if that's successful, I think I might as well just actually start the training then, maybe. But yeah, so we're basically testing like, so the first thing to do is to extract some logic that's taking the, like getting the policy from the tensor, right? Because right now we have a get policy and value. So let's kind of like, let's extract that to just get value, like create a helper function that like it calls. Okay, so this is the function, right? And now what I want to do here is I want to kind of take this and then below it, right below it, I'm going to export another function, which is like get policy from tensor, right? So our tensor will be in a game state, of course, right? So game state or just like that, or game state. Well, first you have to pass in the tensor, which is tf.tensor, right? Or let's kind of go back down, like get policy from tensor. So you see like convert policy to tensor, like kind of returns tf.tensor, just like that. kind of the inverse of that, like convert tensor to policy. Shit, let's just call it that. Policy tensor. So this is convert. So kind of copy the name and kind of like change the name to like convert, and then just kind of like this. Oops, sorry about that. Wait, no. Paste that there, and then kind of copy this and paste it there. So convert tensor to policy. So from convert policy to tensor, we're gonna like do the inverse, convert tensor to policy. And then to do that, what we're gonna do is we're going to like take, so like basically this whole stuff right here, or except for value data, like it's kind of like take all this code right here and just delete that and kind of migrate it over to here, and then kind of return just new policy of that, just like that. Okay, so then what we need to do now is I think just take the policy tensor and kind of let's just do like this. Policy data equal prediction. Wait, no, sorry. Let's copy that over. Policy data number array equals the policy tensor. I think data sync is from a tensor, right? Policy, oops, shift paste. Okay, so that's our policy data. And then we like, this is the same exact thing, we're building a thing. So then what we're gonna do is a convert tensor to policy. We're just kind of extracting that thing, and then we pass in the policy. Wait, what am I doing? Policy tensor is the prediction of 0. Prediction of 0, and then we pass in the game state. The game state. Is the prediction of 0, and then the value data of 0. Let's just inline that. Oops, sorry about that. That whole thing is the value data, right? Wait, what? No, whatever, I'll just leave it as is. No need to inline it. Okay, so now the idea is that like we kind of extracted some of the work into this function right here, convert tensor to policy. So then we're kind of like gonna use this and like use convert policy to tensor to kind of like just as a test, right? Okay, so then let's kind of like close that and let's open up our Scratchpad as well. So we have like some get policy and value, get move velocity from move dir. Let's also get some more commands. Convert, search for that. Next. Wait, so why do we have this? Let's just delete those 2 lines. There's no need for them anymore. So convert tensor to policy. We're gonna want that. Okay, and convert policy to tensor as well. Like that. Okay, so now we have like the requisite functions. So now what we're gonna do is kind of bring them out. Well, no need to give a comment. Let's just kind of work on it. It's just a scratch pad. So we're kind of rebuilding the policy again from what we did last time. We're just building the policy we just saw, right? It goes 0.5, like this move from player 1's turn on turn 1 to like turn the third turn, right? Okay, so let's see. We have the policy, and then we want to convert it to a tensor, right? Convert policy to tensor. Let's policy tensor tf.tensor equals, paste that, of what? The policy. Convert policy to tensor takes in the game state and the policy, okay. What is our game state again? GS. I think GS next, right? GS next. GS next. And then the policy is just policy. Okay, so now we're converting that into a tensor. And then we're going to let restored or policy restored. Policy restored. It's like P2. Policy equals convert policy, or sorry, convert policy tensor. Convert tensor to policy. Convert tensor to policy. Where is convert tensor to policy? You know, let's just be consistent, and let's pass in the game state first as well. Okay, so just like that, convert tensor to policy. Oh, wait, no, we have to propagate its usage. Just like that. Okay, so I think that's good. Just a quick swap in the arguments. So we have the game state, and then we're going to have the policy tensor as well. Convert tensor to policy. Okay, so just like that. And then let's console dot or sorry, just policy, and then this. Oh, I just realized something. You see how we're doing, like, we're logging the policy after creating it, and then we're kind of like doing the transform policy? I think what I should have done, in fact, let me just go back and do that, is take this console.log right here, right? And actually migrate it right before this one, just like so. Yeah, actually, that's a very salient point. Because like by printing out the output of the policy, we're basically kind of verifying that the symmetry that transform policy is not messing around with our original policy. Like it's creating a new object. I mean, I know it is because the first thing we do is like policy.clone in the factory method, right? Like the make policy function or something, or transform policy function. But that's the proper way. In fact, let's just do that. Let's just quickly take a step back and just kind of test that. Just comment everything out we just did. Yeah, let's just quickly test that. Please compile. What is data sync? Okay, so what this is saying, so policy data type that is not assignable to number array. So policy tensor.datasync cannot be number array. So let's see. So here what we did to get number array is prediction of 0.datasync. And it had no problem with this line because this was the existing line. But then when we're calling like this function, it has a problem. So this line is okay. Prediction of 0 we can do, and then we can data sync it, and that gives you a number array. Or it gives you some other array, I think like, yeah, float 32 array. And that... So when we're doing this, it understands it's a float 32 array. But then if we kind of like take this and like pass it into here, prediction of 0, and then we call data sync, then it fails. So prediction of 0.datasync, number array, it accepts it. But then if we do this and pass it into this function, so we pass it in as, so this, we're calling convert tensor policy on prediction of 0, right? As policy tensor. Oh, so maybe this type is wrong. maybe by declaring it as TF tensor, it's kind of like messing it up. Maybe I shouldn't even declare it. Maybe I should just like leave this type parameter out, maybe. I'm not sure, to be honest. Okay, that error went away. Sketchpad, convert policy to tensor. Oh, if this, okay, fine. Let's just give it an export. Clear. TSC that scratchpad. Okay, now node scratchpad.js. Again, we're not testing the policy right now. We're testing the symmetry ones because right now we're actually testing the symmetry from last time. But I uncommented because I wanted to like move the log statements after all the transformations are done. So let's kind of just like quickly just quickly take a detour and make sure that these kind of like this points to like you know what I mean, like horizontally. Like, let's verify that. So the first thing is 0.3, then 0.5, then 0.2, right? Like the first policy we get is something is 0.3, then the next move is 0.5, then the next move is 0.2, just in order. So 0.3, so 0.3. Let's quickly look at this arrow. So this 0.3 is in move ID 0. So its move ID is 0. It has some x component and it has 0 y component. That means it's a horizontal line going east for 0.3. That's correct. Then same coin, move ID 7, which means it's going down. And then down means it has both positive vx, that means like going to the right, and then vy is positive, means going down. So it's southeast, which is correct, south and east. And then it's and this is 0.5. And the last one again is move ID 0, just like the first one. Same kind of positive x, 0 y, and 0.2. Just the only difference basically is, aside from 0.2, is the different coin, right? 69 instead of 18. Okay, now let's look at policy transform. So where does the first one go? Like where does this one end up? This one ends up like this one with 0.3 ends up right here, the very first one. Same coin, 18. Its move ID becomes 4. From 0 it becomes 4, which is correct. It has to be 4, right? You know the directions. 0, 1, 2, 3, 4 goes this way, and it is still 0.3. Like we're testing this one and this one right here, right? And it is for coin 18, which is correct. That matches that one. And then its move direction is 4, which means negative x and 0 y, so that's correct. Okay, now time for the second one, which is like, so now we're testing this one, right? So this one we expect to be this one, right? Same coin, 18. Yep, same coin, 18. And its move direction is 3, right? So from move direction of 7, it's now 3, right? 0, 1, 2, 3. See that? 3. So then that's 3. And then it's negative for Vx, which means we're going west. And then negative for Vy also, which means we're going, which means we're going north. So southeast to northwest, basically, right? Like southeast and now like northwest. So like both the x and the y got negated from positive to negative. And it's 0.5. And then the last one, pretty much same as the first one. It's like 0 becomes 4, 0.2, and it's the coin 69. Negative x and 0 y. So that's correct. Okay, so we can comment that back out. Or sorry about that. Scratchpad.ts. Okay, so now that we, like, the only difference I made is I took this line like here, which was originally like there. I just like moved the console.log after we do the test. In fact, never mind. Okay, yeah, let's just kind of bring back the comments. So we don't want to test those. We just tested that. Okay, and let's just kind of like bring this one, the work that we just did this stream, let's kind of bring that back to life. And let's kind of say now using copy paste policy from symmetry testing, test the interconversion of the policy to and from the tensor. Okay, so now we're kind of like testing this. So like first we get the same policy, and then we're just going to convert it to a tensor. That means like when we're training the network, we are taking the policy, we're kind of converting into a list of size 2400, and we're using that to like train the network as an output. And then to make sure this is correct, right? We can kind of use the inverse operation. If like giving the tensor, we can convert that back to a policy. And if we verify the policies match, then that kind of is kind of testing both these policies for free, or it's kind of like it serves as a test of this interconversion. So okay, let's just yeah, these should be the exact same thing. They use the same game state. They should be they should yeah, they should work. So let's hope that they're the same. Or yeah, TSC that. Cannot find name policy transformed. Oh, it's policy restored, isn't it? Policy transformed was a copy paste from the symmetry case. Policy restored. Okay, good. Now let's compile it and let's test it. It's a lot of stuff. Policy transformed. Huh? Why is there so much here? Oh, because it has all the it has everything that's like it's saying like make these moves with 0 probability, right? So we want to kind of remove the ones with 0, right? Oh, I see what happens, right? Like it's kind of like, okay, like you get the point, right? It has, I'm guessing it has like the relevant ones we care about, like, but it also has like it's like 0.300000. So like, okay, we're gonna actually have to search it. So this one BDB, like 0.3, and then move ID 0, raw value like the X, and then 0Y. So it's kind of like kind of manually eyeball it, right? Same thing BD whatever, move ID 0, some X, and then 0Y, and then it's like 0.3 and then a bunch of zeros. So it's like, okay, yeah, that's good. Then the next one for BDB, like we're testing all the directions, is like this direction, move direction 1 is 0, then move direction 2 is also, wait, should be also 0. Yeah, move direction 2 0. They should all be 0 up till 7, which should be a 0.5, right? Then BDB 2, BDB whatever is 3 is this direction is 0, and then its direction 4, it's 4 for that BD coin is 0, and then same coin 5 is also 0, and then 6 is also 0, and then 7 is 0.5, right? So it has positive y, positive x, and positive y, and 0.49999, which is basically same as 0.5. So that's great. It's very good. And then our next coin, this one 86, which means that like wait, sorry, I just lost where I was highlighted. Oops. Yeah, 0.499, right? So this coin, they should all be 0 until coin 86. So 2E should all be 0. So in 2E, because for so in 2E, is for direction, move ID 0 is 0, move ID 1 is 0, move ID 2 is 0, move ID 3 is 0, move ID 4 is 0, move ID 5 0, move ID 6 0, move ID 7 and 0. Okay, now for the last one, right? And now for the remaining things, for the final coin which we care about, of 86, right? Because in the original one, okay, so we have 0.5, then we have 86, and that is move ID 0 is 0.2, and then the rest shall be 0. So this one, 86, move ID 0, and then like this one, positive 0 is 0.2. So that is correct. And the rest should all be 0. From here to the end, for the remaining move direction, shall all be 0. So 86, move ID 1 is 0, move ID 2 is 0, move ID 3 is 0, move ID 4 0, move ID 4 0, move ID 5 0, move ID 6 0, and move ID 7 0. Okay, so that looks good. Okay, status, get add all. Now it's kind of, okay, so then get status, v scratchpad.ts. Now let's kind of like, yeah, let's just comment that out, and I'll just add a note to myself. Note that the policy restored has like 24 entries, 21 of which are moves with 0 prob, right? And the 3 that aren't 0 are super close to the original probs, like 0.5 in policy became like 0.49999 and so forth. So seems to check out. Okay, so now I think we're actually get status, get diff, just a little comment that we did. Okay, so then let's just do a get add all status. So now we have just basically well, we extracted one of the functions to create helper functions. Never mind. I guess tensor. Okay, so I think now like we're kind of like done like kind of testing the whole policy and vector and back and forth vector back to policy. So I think that's actually a satisfactory point. So for now I could just delete that, and I could just end the stream here because yeah, that's a good test. Like we're basically like one by one like testing a bunch of like, because like we had a working AlphaZero for Connect 4, and then we kind of like did BumperCoins from the ground up, like kind of swapping out all the components in Connect 4 like game state move policy, and kind of like swapping them out for BumperCoins versions of them, discretized BumperCoins version, like a discretized variant of BumperCoins, taking that game and like kind of like copying and pasting like the same entities like game state move and policy, but for BumperCoins, just, and then like kind of all these components, and especially net.ts, which kind of connects them. And then we're kind of like testing each of them like kind of one by one, so that like if all the components work as intended, as expected, then in theory we just kind of like, we copied over the mcts and train.ts files, and we're just basically like doing a swap out for the C4 components for the BC components, and they should like just swapping out one game for the other one game logic for the other game logic, and like neural net logic operating on that game logic, and just like kind of like swapping in all the sorted components that we want, swapping them out, and everything should just work magically. So I just have to like, so I think we're almost done, almost ready to get started in the actual training. But yeah, we just like we just trained like two central functions, which is like converting the policy that we get from the Monte Carlo policy improvement to an actual vector, a vector that we can use to train a neural net as like a suitable output. And then like given the output, we can kind of convert the output back into a policy, like in the Monte Carlo tree searches crate node, like when we're actually evaluating the game state by getting like spitting out the policy output from the policy head and the value head. Like from the policy head, we're getting like that same kind of like list of like 20, like the same policy tensor, and then we're like converting that back into a policy, and we have to do that in our like during our MC in our Monte Carlo tree search when we hit the leaf node in the base case, when we actually like, yeah, you know, I've talked about this before. So like basically like, those are like two central functions of like get policy and value and convert policy to tensor, or like kind of like two inverse functions. I extracted a function which I called like, so convert policy to tensor. I extracted a function I called get tensor to policy, and then I kind of like verified that and get policy to tensor were inverses. So like this kind of like is testing like two central functions in net.ts. So like, and then yeah, so I think that's pretty good progress. Because again, like, what are all the functions we have? Like ls grep ts. How do I do this? Wait, what? Okay, yeah, like this, right? Like coin.ts, fixed point.ts, like game state, forget those two. So we have like game state, then we like tested apply, like so like we have like these functions. Actually no, for now I'll just stop and be satisfied with like testing testing two important functions in net.ts, and that'll be all for now. Well, later.